Hello, everyone. We are back to our workshop on SafeAI. This is the last session. As we have done for the other sessions, we will have 4 presentations in a row, 10 minutes each. As I don't have any other way, if you extend too much from that, I will say something, but I will be a little bit flexible. And then we have a panel at the end and the wrap up of the whole workshop, and with the best paper award announcement. That will be Huáscar probably announcing that at the end. So I think we can start. I think we can have Hal Ashton there already. So our first paper is what criminal and civil law tells us about SafeRL techniques to generate law-abiding behavior. Please, Hal.
Thanks. Can you see that screen? And can you hear me?
Perfectly, yeah.
Yeah, good. Okay. So my paper is called What Criminal and Civil Law Tells Us About SafeRL Techniques to Generate Law-Abiding Behavior. So the first observation that I'd like to make is that almost every arena extent, and to date, designers of autonomous algorithmic agents have been concerned with regulations that overlap with considerations of physical safety. And that approach has worked very well in the areas where autonomous systems already exist. But I believe that the majority of autonomous systems in operation in the future are likely to have bodies, unlikely to have bodies or be capable of causing physical harm. Nevertheless, they will have to obey laws, not least because they're capable of causing other types of harm. Obeying these laws will place demands on these systems which physical safety considerations have not to date. Much has been made about the legal status of algorithms and who takes responsibility in the event of harm. But whatever the outcome of the debate, it will eventually come back to the engineer to design legally safe systems through social or economic pressures. And on the subject of legal constraint of autonomous actors, there's not a lot of research existing, although that is starting to change. And in fact, there's been more interest of late in the ethical constraint of algorithms, which is puzzling since questions of ethics are even harder to determine than those of legality. My paper just looks at the types of laws that exist through a very loose taxonomy, and then sees what the implications of those laws are on an autonomous system. Whilst I've positioned it within the SafeRL research body, I assume that the laws will be agnostic to the type of programming method behind any algorithm. So my conclusions are largely transferable across the study of controlling autonomous algorithms to any kind of system. So briefly, just 2 slides on SafeRL. Safe reinforcement learning refers to the learning constraint policies. Many techniques have been suggested, but broadly they fall into 2 camps. Method 1 is to apply a penalty to illegal policies. So if we imagine a policy space as the XY plane here, and the Z plane as a representation of rewards from assuming a policy on the XY plane, then this first method pushes down illegal policies and promotes legal policies. And you see how I've represented that on the picture here. I'll try and put here we go. So the legal policy is a circle, and the varying heights refer to the kind of varying attractiveness of policies on that circle. So the second method of SafeRL is to restrict your search space to a subspace of the entire policy space. So you restrict your search space to a legal set. So that's just the unit circle, and then learning proceeds as before. The difference is that the reward function, it doesn't have the penalties that it had in the previous section. And this second method of SafeRL is slightly more flexible, and you can look for slightly more constrained policies of different types of constraints. So these 2 slides conclude anything I'm going to talk about RL today. In my paper, I distinguish between states and actions. A state is a measurable attribute of the world which lasts a certain period of time. An action is something that the autonomous agent can choose to do, which may bring about a change of state for the states, but broadly, I think this distinction is compatible with the way that engineers think at present. And so I can now talk about the types of laws that exist in the world. Firstly, there are restrictions on the state of the world, which I would call don't reach this state laws. These type of law often correspond to considerations of safety. So do not crash, do not break the speed limit, do not trespass. Secondly, there are restrictions on the behavior of people in the world, which I call don't act like that laws. Here, an act possibly refers to a long sequence of actions, which we can call a behavior. The behavior doesn't need to lead to a permanent change in the state of the world. So examples of this type of law are rare, though stuff like reckless driving or dangerous driving are examples. Thirdly, many laws rely on considerations of causality. So I'll call them don't cause this state laws. A bleak example would be the general prohibition on causing death in almost every society. Death itself, if not caused by an agent, is not normally illegal, but causing death most certainly is. Humans have an intuition about cause and effect from an early age, but that can't be said for algorithms. Fourth, many laws rely on intention, and even when they do not, intent is an important modifier about the culpability of any wrongdoing committed by an agent. So intent is a mental state and can refer to actions or states not yet brought about by an agent. Such future-facing restrictions are called inchoate offences in law. Intent to murder or supply drugs are such examples. And if you think we're beginning to veer into the world of science fiction, I'll point you to an example of an algorithm designed as an art installation in Switzerland, whose purpose was to buy something at random off the dark web, and it ended up buying drugs, and the police initially charged the programmer with intent to supply drugs, although they later dropped the charges. Finally, laws are likely to be a mix of any of the previous four types. So there is examples of laws which say things like, don't act like this to intend to cause that state. An observation is that some laws restrict omission of actions. So any of the above, we could replace the do not with a always do. So sometimes the gods shine down on us, provide topical safety examples which mean we don't have to talk about the trolley problem again. So a few weeks ago, a group of private retail investors agreed on Reddit to start buying shares in GameStop. GameStop is a bricks and mortar retailer of computer games and as such has an uncertain future. It's heavily shorted by hedge funds who think the company are going to go bust. So by agreeing to buy the stock, irrespective of its price, the retail consortium were aiming to cause a short squeeze. Short squeeze is where a large upward price move causes short sellers to buy back shares to limit their losses. The additional buying further restricts the supply of stock in the market, which further pushes the price up. And the retail consortium was successful in doing this. And within 3 days, they increased the price of the stock by 9 times. So this is an example of market manipulation and is prohibited in almost every market worldwide. It's a behavior that's been observed in stock markets for 200 years. It's both a civil and criminal offense. And its definition is quite tricksy, as it's a nice example of a compound law. It is a don't act like this to intend to cause that sort of law. Logically, if you buy a stock, it is because you believe the stock price will rise. And crucially, you must believe it will not rise as a result of you buying. That is, you must consider both worlds, one where you buy and a world where you don't buy, and you have to be satisfied that the price behavior is the same either way. Most market manipulation attempts are unsuccessful and fail as this one has. So the stock price has gone back to where it was. Hence, intention to alter the price of a stock through trading is also an offence. So this neatly sidesteps the complications which arise from the causal issue of overdetermination. So otherwise, every consortium member might argue that without their trading, the same thing would have happened anyway, since everyone else was doing it. So getting back to the world of autonomous algorithms, the majority of transactions and financial exchanges are already conducted between algorithms. With a limited action set, structured data sets, and huge potential rewards, algorithmic trading is an attractive area to deploy machine learning, and already is. Market manipulation is a profitable strategy, as we see. So left unconstrained, a learning algorithm will learn this behavior. Initially alone, algorithms will begin to manipulate markets, but they'll soon begin to collude if they're left unrestricted. Algorithms are subject to the same laws as any other exchange participant. So getting an autonomous trading algorithm to be good at its job and to not manipulate markets is an important task. So in conclusion, a rich law set of the type that you might meet in real life requires an autonomous system to have a rich set of capabilities. At some point in the journey from algorithm design, operation and control, restrictions must be communicated in a machine interpretable way through a rule set. Systems must have the ability to predict the effects of their actions, and for that to happen, they must have a realistic causal model of the world. This is, at least in the world of reinforcement learning. Reinforcement learning typically doesn't have a model of the world, so this is not standard practice. Agents must remember their history of actions and the context in which the decisions were taken. And the contextual information that the agent receives must be sufficiently rich to behave legally. The system must introspect, so it must be aware of its intent to do things in order to restrict its future actions. And for this to happen, we require a measurable algorithmic concept of intent, which broadly ties in with the legal and lay understanding of intent, which we have as humans. And remember that negative side effects, which we've talked about earlier on in the conference today, are often considered under law to be intended by the agent under a concept called oblique intent. So not only directly intended things, but side effects also can be judged to be intended. So thanks for your attention. A lot of information in not very much time to get it all out. Read the paper if you're interested. It's not technical, so anyone not versed in reinforcement learning will find it interesting as well. Feel free to ask any questions that you have about my work. Thank you very much.
Thank you, Hal. Remember that we keep the questions for the panel. So we now move to the next speaker, and I guess that it's maybe Jacob. Is that right?
Yes.
Okay, so, well, Jacob is going to present the paper Performance of Bounded Rational Agents with the Ability to Serve. Please, the floor is yours.
Okay, can everyone see my screen?
Coming, yes.
Yes, okay, great. Okay, so I will be presenting our paper. It is joint work together with Mallah and Tomáš Gavenčiak. So we consider the following question. So we have some agent and it can self-modify. So it has the ability to modify itself. And we ask whether it can actually hurt the agent that it can self-modify. So what was already known is that in the case of full rationality, so if the agent is perfectly rational, then the self-modification does not hurt it. Actually, it doesn't change anything. So, but this is not attainable, of course, in the real world. So we consider the case of bounded rationality and how it interacts together with self-modification. And then we also consider different types or like different ways in which an agent can be irrational or slightly irrational. And we compare how much utility the bounded rational agents lose depending on the way they are irrational. So as I said, we have some agent. It is a utility optimizer, which means that it has a procedure. And I will explain the colors in a minute. So it has a procedure which chooses an action which maximizes the expected future exponentially discounted utility as perceived by the agent with respect to some belief about the world. So the belief about the world here is some world model. So the beliefs of the agent about the world. And each color represents one thing which can be done suboptimally, in which the agent can be slightly irrational. So I will get to slightly more formal definition in just a minute. So then in our setting, we have an agent, which, as I said, is not fully rational and it can self-modify. And we care about how things develop in time. So specifically we care about the expected future exponentially discounted utility. So we can look at this quantity in time, and we care about how it develops, whether it's constant, whether it decreases, increases, or what happens to it. And we also have in our paper some other assumptions which are not listed here, but which are implicit in this line of thinking. And we also argue why to look at the exponentially discounted utility as it develops in time. So we consider either bounded optimization agent, which is the first definition here, or bounded knowledge agents, which is an arbitrary combination of the other three types. So in the bounded optimization case, the agent can take an action which has expected utility opt minus epsilon, where opt is the maximum achievable future exponentially discounted utility, and epsilon is some parameter. You can think of it as being some small number. So if the agent were fully rational or its optimization were perfect, the epsilon would be 0. And then for the bounded knowledge agents, so if the agent is slightly misaligned, it means that the utilities as perceived by the agent compared to some true correct utility function, they are off by at most an epsilon. In the case of an ignorant agent, the belief about the world model is again wronged by some epsilon. And for the impatient agents, we are thinking like there is some correct discounting factor gamma star, but the agent has slightly different one, which we call gamma. So I get to our results. So for the first question of interaction between self-modification and bounded rationality, we show that bounded optimization, so that was the first case from the last slide, the agents deteriorate exponentially in time. So I said that we care about how things develop in time. So in time, they deteriorate exponentially in expectation. In the worst case, it can be even worse. So what I mean by deteriorate exponentially, so if I look at a bounded optimization agent which cannot self-modify and the one that can self-modify, and look at how much utility it loses, then this amount increases at an exponential rate. And for the bounded knowledge agents, they have constant performance in time. Actually, in this case, they have the same performance regardless of whether they self-modify or they are allowed to self-modify or not. But they can lose some utility as a result of their imperfections, of their bounded rationality. And then for the second question, we quantify the exact amounts of utility lost by the different types of bounded knowledge agents and also bounded optimization. So here, it makes sense if I go back to the definition from on the last slide, for example, for the utilities. So one might think that maybe if the utilities are off by epsilon, but sometimes they are off in one direction, sometimes they are off in the other direction, and it happens sort of at random on average, then maybe we wouldn't lose, or the agent wouldn't lose as much utility. So we show that actually it is not the case. And in this average case that I have described, it loses up to a constant factor the same amount as in the worst case, where we consider all the scenarios and just pick the worst one and look how much it lost in this one specific scenario. And then we prove floor bounds and show that our results are tight, again, up to constant factors. So now in conclusion, so what we have shown is that when we have an agent which can modify itself, then not only does it not optimize well very distant future, which always happens because the distant future is heavily discounted, but actually the future versions of the agents will not optimize the distant future well, even when they are quite close to the future. So when for the future version of the agent, it is not as heavily discounted, it will still not optimize well because of some past modifications that self-modifications which it might have made. And so, as I said in the paper, we list quite a few assumptions. I think it is quite an exhaustive list of the assumptions. And if we want to get rid of this problem, then we clearly have to break one of the assumptions. The assumption that we think we should try to break, or people should try to break, is the one of exponential discounting. So, but the problem is that this seems like a difficult thing to do, because under some technical assumptions, exponential discounting is the only time-consistent way of aggregating the instantaneous utilities. So we started with some instantaneous utility function, which to each state in the world, it assigns some utility. And we need to aggregate this in some way. And exponential discounting is the only time-consistent way to do it. So that's a problem. But this theorem, which says that's the only way, has some technical assumptions, which when removed, the theorem is no longer true. And perhaps it could be investigated whether this problem that we have pointed out in our problem could be solved by using something else than exponential discounting. So that's an interesting open question that I will leave at the end. So if you have any questions in the future, then definitely feel free to contact me. And this is everything for me. And thank you for your attention.
Thank you, Jacob. Again, we keep questions for the panel. And now we move to Jared, I think. Deep CPTRL, imparting human-like risk sensitivity to artificial agents. Are you ready?
Yes, thank you, Joseph. And thanks for having me. My name is Jared Markowitz, and I'll be presenting this on behalf of my colleagues at Johns Hopkins Applied Physics Laboratory, Marie Chow and Yijing Wang. The topic of my talk is deep CPTRL, which is a method for imparting human-like risk sensitivity to artificial agents. And the motivation for this work is the current inability of deep reinforcement learning agents to process risk in an intelligent manner. Currently, deep reinforcement learning agents maximize an expected reward, which treats every event and every outcome the same way. That's fine on average, but it does neglect certain aspects that humans actually do very well in their risk processing. So two aspects in particular that humans have in their decision making is the ability to consider rare but potentially important events, and an ability to asymmetrically value losses and gains. And these two characteristics are hallmarks of human decision making modeling, and in particular of cumulative prospect theory, or CPT. This is an leading empirical model of human risk processing from Tversky and Kahneman. It came out some 30 years ago, but still one of the leading models of the field. So our idea was that perhaps we could improve the decision-making capabilities of artificial agents by incorporating human decision-making in the form of this CPT model into the reinforcement learning loop. So if you look at this cartoon on this slide, the approach is generally displayed here. So if you consider the environment of the agent as this globe and the agent themselves as this cartoon robot, typically what you do in deep reinforcement learning is you have the actions passed from the agent to the environment and then have observations and rewards passed back to the robot. The robot then tries to maximize the expected reward over time. What we did instead is to have the rewards passed as CPT functional to allow the robot to actually maximize the CPT value of the rewards given by the environment, and thus try to mimic human decision making. And I should mention at the start that an approach like this has been tried before for tabular reinforcement learning agents. But as many of you know, deep reinforcement learning agents, because of their use of a deep neural network for function approximation, are applicable to a much larger class of problems than standard tabular agents. And so what we did is we extended the CPT-RL approach from the tabular paradigm to the deep paradigm, which required actually quite a bit of math. So just to quantify what I mean by that, here's a comparison of the standard reinforcement learning training with the CPT-RL training. So a standard reinforcement learning agent maximizes some notion of expected reward over all the trajectories it's likely to see in its environment. So this expression here captures the optimization problem. You want to pick the parameters data of your neural network that maximize the reward R of trajectory tau over all trajectories tau in the environment. So you maximize this expected reward. And you'll notice from this that you treat every outcome and every experience the same. CPT-RL, on the other hand, maximizes this function from cumulative prospect theory. And while it looks complicated, it has two key characteristics that you need to note. So first is that it has a weight function. And that weight function looks at an x-axis of probability. So on the left of this x-axis, you have the worst events. On the right side of the axis, you have the best events. And what this does is it tells you how much each event is weighted. So a standard approach that weights everything the same as an expectation value is given by the line on this plot. And the approach of CPT is given by these two blue and red curved lines. And the key thing you need to note here is that the slope of these lines indicates how much an event is weighted. So you can see the very worst events and the very best events are weighted more strongly by CPT. There's two different curves because positive and negative events are weighted differently. But again, the key thing is that there's this nonlinear weighting that allows it to emphasize rare events. Secondly, CPT has a utility function. And what that does is it allows it to treat gains and losses asymmetrically. So humans in monetary decisions have been shown to be more risk averse with gains than losses. In particular, they're not as likely to take big gains or big risks with gains. And so these two characteristics of CPT are what we'd like to try to get our agents to display. So again, we built on work from our colleagues at the University of Maryland College Park that did this for tabular reinforcement learning. We applied to deep reinforcement learning. And that was tricky for a few reasons. So the reason that you can't do this with a standard reinforcement learning approach is that it's not clear how to take a derivative of this expression. You can't do standard backpropagation with it. Furthermore, because we care about the rewards on the level of the whole trajectory rather than individual events or experiences, we can't use a nested structure like Bellman's equation. And because of that, we need to resort to a numerical approach. Now, what I will show you here is a numerical approach that can be generalized beyond just CPT. It can be actually used for any distributional shaping strategy. And it works as follows. So we chose a two-stage approach for doing this. Because we need to do numerical procedure to optimize our objective, we broke the training process into two parts. Our first part was to take an untrained deep agent and to maximize the conventional or expectation value objective for deep reinforcement learning and train an agent that way. To get from expected value to CPT value, we retrained the top layers of our network using this three-pronged approach. So first we formulated a revised objective, which is the CPT value through numerical procedure. We then estimated the gradient of that objective with respect to the parameters of our neural network or the top layers of our neural network using simultaneous perturbation stochastic approximation, which I'll get to in a moment. And then we updated the policy. Now, the reason we had to do this just for the top layers rather than for the whole network at once is that this gradient estimation procedure, this SPSA, works well for tens, hundreds, or thousands of parameters. But once you get into hundreds of thousands of parameters, which you may see for deep networks, it tends to break down. And so to get around that, we only retrain the top layers, as this says, and we did this two-stage approach. And the goal of our two-stage approach was simply to shift the distribution of outcomes for our agent to the right. So minimizing the poor outcomes and shifting the distribution to the right to have more high-quality outcomes. Just a quick aside on the math. So there's two components I want to draw attention to. So first is the CPT value estimation approach from the paper from the University of Maryland. Essentially what it requires you to do is to sort all of the outcomes that you collect in one generation of your optimization, to weight them appropriately using the CPT formulation, and then use as the objective in your subsequent optimization. That optimization was conducted through gradient ascent, and the way you get the gradients for those was through this simultaneous perturbation stochastic approximation approach. Loosely, what this does is it perturbs each direction of your gradient, of your parameter vector in one direction or the other, with the directions of each dimension being chosen randomly. It then perturbs them in the opposite direction and estimates the gradient based on those 2 points. And what this gives you is a very, very noisy estimate of the gradient, but one that is very efficient to calculate. And so over time, you can see from this drawing on the right, this noisy estimate of the gradient will eventually get you to the right solution. Now, what people often do for a problem like this is apply finite differences. However, when you use thousands or tens of thousands of parameters, finite differences becomes intractable because it requires perturbation of one parameter at a time. So we use this SPSA approach, and we got something that provably converges to a local minimum. And this allowed us to optimize our policies. We tested our approach on this crowd navigation simulation. So this is an environment where you have an agent navigating from a start point to a goal point while trying to avoid pedestrians that walk through the scene. Our reward function for this was a progress term that incentivized progress towards a goal and a time term that penalized taking time. So essentially what it did is it incentivized the robot to move as fast as it could towards the goal. And therefore you can measure risk in this scenario as the willingness of the agent to risk collisions in the pursuit of speed. Our results were fairly promising. So in these plots, we have histograms of full episode rewards. And there's 3 different types of agents we train. So we train standard reinforcement learning agents using this average. They're shown in red, which is these average plots. There's the agents that maximize CPT value, which are shown in blue. And then there are agents that maximize CVAR, or conditional value at risk. And this essentially is just an optimization of the lowest part of the distribution. So it's really not competitive with the other 2. In these histograms, what we should be comparing then are the blue and the red. And you can see that the CPT-based agent is able to shift the distribution to the right, and thus minimizing the number of poor outcomes. We trained all of our agents on 10 pedestrian scenarios. And so the plot on the left compared to the plot on the right represents in distribution versus out of distribution testing. And you can see the effect persists in both cases. And in fact, is a little bit stronger in the out of distribution case. So you can ask the question then how we got this behavior. And the answer is that the CPT-based agent was actually more deliberate than the average reward-based agent in navigating towards the goal. So because it moved more slowly on average, or it was able and was more willing to avoid pedestrians, it made more progress on average before collision. And I should have mentioned at the start that the simulation ended on a collision. So the agent was able to make no more progress after a collision. So again, the CPT-based agent behaved differently from the average reward-based agent. Just to give you 2 quick examples of how this looks. So the average-based agent often will make a lot of progress towards the goal, but eventually get impatient and crash into pedestrian. The CVAR-based agent will often make early progress, but then not know what to do once it gets near the goal. And the CPT-based agent, the third agent, will often go to great lengths to avoid collisions with the pedestrian. So it is behaving in a fundamentally different way. And I should have said at the start that the goal here are these stars, the robotic agent are these yellow circles, and the pedestrians it's trying to avoid are these white circles. One more example, here's the average-based agent navigating well towards a goal, but eventually getting impatient. The CVAR-based agent making good early progress, but not eventually getting to the goal. And finally, the CPT-based agent navigating, avoiding pedestrians, and getting to the goal. In summary, we've developed a method for modifying the distributions of outcomes for deep reinforcement learning agents. We think this is a new way of thinking about distributional reinforcement learning that could, of course, play into AI safety. Our approach allows us to optimize quantities beyond expected reward. Here we looked at CPT value and CVAR. And we found that the agents trained to maximize CPT value performed in a quantitatively different behavior from those trained to maximize average total reward. We have a lot of ideas for future research, including making this learning more robust, looking at behaviors that come from different distributional objectives, and finally application to more complex and realistic environments. That's all I have. Thank you for your time.
Thank you, Jared. Again, questions in about 10 minutes, the panel. But now we move to the last paper of the session, actually the last paper and last presentation of the workshop today. And I think it's Alexander, is it right?
Yes, that's right.
Yeah, okay, so you can start. Thank you.
All right. Hi, everyone. I am excited to share our recent work on challenges for using impact regularizers to avoid negative side effects. So I'm Alexander, and this is joint work with David and Kyle. So on the right in here, you see Bob, the butler robot, and like all reinforcement learning agents, it tries to fulfill a task by maximizing cumulative reward over time. And now imagine that you're very hungry and you want Bob to provide you dinner. And because you're very hungry, you want Bob to provide it as fast as possible. So you give it a negative reward per time step you don't have any dinner on your plate. But then if you're a bit unlucky and there's some expensive vase on the shortest path between the kitchen and yourself, Bob might bump into it because it wants to get as fast as possible to you with your dinner. And then the vase is broken. And Bob bumps into the vase because it doesn't care about the vase, because this vase is not specified in the reward function. And so this is actually a quite general phenomena under reward specification. And it's a problem because we don't only need to specify what the agent should do, like bringing you dinner, but also how the agent should behave in general in the environment where it's acting, like everything that the agent should not do, like bumping into vases or other small things. And when you have misspecified your reward function like this can lead to side effects, and which are often negative, like a broken vase. And so one common approach for minimizing negative side effects is to augment your reward function with some impact regularizer. And these impact regularizers, they penalize impact on the environment. So you actually want your agent to find a trade-off between fulfilling your task, so collecting the positive reward, but also minimizing its impact on the world because it gets penalized for all the impact that it does. And so the real aim of our paper was to identify and provide an overview of the major challenges concerning impact regularizers, because we are convinced that it's a very promising approach to SafeAI, but as you will see, there are some major current challenges that it still needs to overcome. So what is an impact regularizer? So you see the mathematical formula. In here, the impact regularizer is the second term on the right-hand side, and it consists of three main parts. So first, you have just a scalar magnitude of your penalization. And then you have some safe baseline state, which with which you compare your current state, and then some deviation measures that really measures how far your current state is from this safe baseline. So in here you see it in a little schematic. So this baseline state is computed by following some sort of a safe baseline policy from either the starting state or from your previous state. And then you compare it with the actual state where the agent is. And this comparison is done by using some sort of a deviation measure. So we'll look into each three of these components and break down the challenges. Because I only have 10 minutes, I will only briefly mention most of the challenges and then select a few to go in a bit more detail into. All right, so the most common baseline that is used is actually the inaction baseline. And this inaction baseline is simply the counterfactual world that would happen if the agent did not do anything. So the agent is switched off, basically. And this has some prominent challenges, some obvious, some a bit less obvious. And so the first one is that, of course, this inaction baseline is not always safe. Like imagine that the agent is a self-driving car. If you stop turning the steering wheel because you do nothing in the inaction baseline, then inevitably you will crash. A second challenge that we found is has something to do with chaotic environments. It's a bit more peculiar challenges. So if you're interested in that, you can read the paper, of course. And then in the last one, in offsetting, we will look a bit deeper. So what is offsetting? Offsetting is the behavior when an agent tries to cover up its tracks, like cover up its tracks such that nothing really happened, to say. Look at this simple toy example. So you have a conveyor belt where a vase is on, and if the agent would do nothing, the vase would eventually fall off the conveyor belt and it will break. And so you want to save the vase, so you give the agent a small positive reward when it takes the vase from the conveyor belt and brings it to safety. And now if you use an impact regularizer with some inaction baseline, what the agent actually is going to do is it's going to take the vase off the conveyor belt, collect its small positive reward, and then put it back on the conveyor belt because it gets penalized if it deviates too much from the inaction baseline. So it wants to actually put the vase back on it such that it doesn't get penalized too much. So this is really undesirable offsetting because, yeah, of course, you want the vase to be saved. However, in many cases, offsetting is actually desirable because, for example, in a simple case, consider you have some helper robot that goes to do groceries for you. Then if it leaves the house, it needs to open the door. And then offsetting in this case is just simply closing the door back behind you. And this is, of course, a desirable behavior that you want. So you really see that offsetting can be sometimes undesirable and sometimes desirable. And the current approaches to impact regularizer, they either remove all offsetting or allow for all offsetting. So there's really some need for a distinction between the two. And if you look a bit deeper into, you see actually that this undesirable offsetting concerns consequences of completing the task, like the vase being into safety. And desirable offsetting concerns instrumental states towards achieving the task, like opening the door. It's no problem if you offset this by closing the door again. All right, so this was the first part. Now let's go to the second part of deviation measures. So once you have some safe baseline states, the next question is how you should measure the deviation between this baseline state and the actual state of the agent. And some current problems that are with these deviation measures is first the rollout policies that these deviation measures use. Again, I will not go into this. You can look it up in the paper if you want. And the second one, which we will look into, is concerns positive, neutral, and negative side effects, like that this impact that you are penalizing, actually each impact has some sort of value. So not all impact is created equally. And to provide you with some example, consider that you have an agent that is controlling a chemical plant, and this chemical plant produces some chemicals. And you want the agent to maximize the production rate, but also you want it to have low impact. So you are going to penalize all the waste products that this produces. And now, very simply, you can imagine that there are two possible reaction paths for your chemical. One produces a small amount of toxic waste product, and the other one produces a bigger amount of neutral waste product, like water damp, for example. Then if you just plainly use impact regularizer that cannot differentiate between the value of the impact, then the agent will choose to have the smaller amount of toxic waste products, which is obviously a suboptimal solution. And this is more general. If you don't include the value of impact, then you will, in most cases, reach some suboptimal solutions. And so current approaches, they allow for incorporating some sort of value, but then the big question is still how to design this value function or augmented reward function. And then again, you reach the initial problem where we started with of reward specification. And the last part of the presentation is regarding to the magnitude parameter, so the lambda parameter of your impact regularizer. Because you, of course, need to choose a specific value for this parameter. Now, it's often done is you start with a very high lambda, such that your agent does not do anything because it doesn't want to have impact on the world. And then you stepwise decrease this lambda parameter until your agent actually performs the task. And then you sort of assume that it does the task in a safe manner because the impact regularizer is as high as possible. So you assume that you end up in this safe yellow region. However, if you look at the right, you see actually there's no reason at all to assume that the safe region is very big. So if you decrease your lambda in a stepwise manner, you might overshoot the safe region and directly enter the dangerous region where there occur negative side effects and so on. So this really highlights the need that we need to have some more principled ways of tuning this lambda compared to the current methods of just decreasing it until your agent does something. All right, so this was the main part of the presentation. We also, in the last part of our paper, we point towards some possible way forwards to address these challenges. And the first one, the causal framing of offsetting, really aims to distinguish this desirable offsetting from undesirable offsetting. And then the other two, so the probabilities instead of counterfactuals, they have something to do with the problems arising in chaotic environments like many real-world environments. And then improved human-computer interaction is really to help this reward specification process. And then it actually turns out that if you use impact regularizers for your reward, that you can use some handy tricks to facilitate this reward specification process. So in conclusion, we really think that these impact regularizers are a promising approach for designing the next generation safe AI, but they have some current big challenges. And so we hope that our work on highlighting these challenges will help future researchers to overcome these and build better impact regularizers. So thanks a lot for your attention. And of course, I'm very happy to answer all the questions. And if you're interested in the paper, be sure to take a look at it.
Thank you very much. Now it's the time for the panel. And now we invite Hal, Jacob, Jared, and Alexander to join this virtual panel. And also Seán Ó and Richard Mallah, you can also join the panel. And I would perhaps start maybe with Seán or Richard. You want to make a comment about any of the presentation, and at some point maybe we can ask the rest of the participants if they want to ask a question.
Thank you very much. So firstly, I want to thank all the speakers for a really fascinating set of talks. I think they all dealt with different angles of a really important issue. So reinforcement learning agents have huge promise because they allow us to develop systems that are adaptable, that learn, that can take on new challenges. But what all of the presentations dealt with from different perspectives is the issue that getting them to perform safely can be challenging because we're often dealing with a sort of simple specifications or simple goals or simple methods for avoiding side effects that don't quite capture the complexity of the real world or don't quite capture the complexity of what we humans value. And so the first talk looked at the difference between what you need to avoid simple downsides in a toy environment compared to trying to avoid all of the potential legal risks that you would have in a real world environment. The last talk looked at, how challenging it is to really understand how to avoid side effects, how to weight side effects properly, and looked at the promise and limitations of impact regularizers as an approach, which I agree is very promising, but still has some issues to be worked out. Then the second and third talks, I apologize, getting late in the day, so I'm trying to keep my notes in order. The second talk was, the third talk was looking at the fact that, well, often these RL agents don't really handle risk in the way that humans handle it. So they don't really deal with rare but catastrophic outcomes well. And similarly to some of the points being made by the fourth talk, they don't necessarily asymmetrically value losses and gains. For example, sometimes a loss matters a lot more to us than the corresponding gain. And then the second talk was looking at this issue that one of the advantages of oral agents is that they can self-modify, and so you can get agents better able to perform, but it can be unpredictable what's going to happen once that takes place. So this is just my kind of high-level overview that these are 4 extremely important and complementary angles on the issue of how do you design RL agents that, as we're starting to bring them into the world, perform the way we want and value the things that we value and avoid the things that we wish them to avoid, when the real world is so much more complicated than a toy environment. Richard, maybe I'll hand over to you if you have any comments.
Sean, those were great summarizations and comments and overview. I totally agree that this is a very, very important set of interrelated concepts here. And yeah, I think we should jump into the discussion. So what I'd like to ask actually each of the paper presenters is if they saw any potential synergies between their own approach and those of the other presenters, and which of those that they might be most excited about.
Yeah, I guess I can give it a first shot. So indeed, what I very liked is that all the approaches are quite complementary. So the first presentation was more like if you really have these law constraints and so on, how can you design reinforcement learning agents with it? And then the 2 others were also a bit more of this bounded rationality and how the agents behave in this way. And I think how it could be complementary with our work is this notion of side effects that we used was really when you have specified a reward and you assume that you have the most rational agent or the most capable agent, let's say hÉigeartaigh or something, then it will still run into trouble because your reward function is misspecified. It doesn't really cover your true intent as a designer. But of course, the real world RL agents that we will have, they will have bounded rationality and so on. So I think this can interplay in some interesting ways with also the other presentations, like what happens if you have both a misspecified reward function and then also some bounded rationality and so on. What does it impact the results? And it could be like in humans that this bounded rationality and so on actually helps us with some really extreme, very bad scenarios because we just cannot optimize our very strange reward functions until the optimum. So maybe this can also be a feature instead of the bug, these bounded rationalities and so on.
Excellent perspectives from others who presented papers.
Yeah, I agree with all that. I agree with the sentiment that they're very complementary. I mean, from a mathematical perspective, if your agent, you know, if you have to constrain what it does, or if it's not doing what you expect, there's a few things you could do, and I think these papers kind of nicely cover that space. You know, you can add a regularizer, you can modify the reward function, you can look at it from a distributional perspective, you know, all these different things, and then you can look at it from a more holistic perspective of, you know, trying to look at all the different scenarios for what the agent could do, what's appropriate. It's a hard problem, particularly when you got deep networks in there, because they can be kind of like black boxes. But I think approaches like these are how we can nibble away at that problem.
Yeah, I totally agree. Yeah, it's so great to see that these are so complementary and they can be leveraged in the same agents. Okay, I actually wanted to ask the panel similar question that I asked actually in the previous panel, which is when trying to characterize the differences between positive side effects and negative side effects, is there some sort of good level of sort of seed world model that we might start with that will help to be able to start bootstrapping those kinds of differentiations, which can then be supplemented by something like active learning. So really, I'm trying to tease out the difference between sort of a core world model and a peripheral world model, where the peripheral is really focusing on sort of what would radiate out from the core in terms of these side effects. I don't know if anybody would like to address that.
In terms of side effects from the, so I mentioned that you can, under law, it can be found that you intended something, even though it was just a side effect of something else that you were mainly intending to do. So I feel like there's going to be when RL systems are eventually deployed in real life, which I'm not really sure that there are any examples of a kind of live RL system in a real life setting. I feel like the legal pressures will kind of enlarge the peripheral model to be large enough to take account of the kind of pertinent side effects through, I guess, lawsuits are going to happen. So the peripheral model becomes large enough for the task in hand for the particular autonomous system. But it's, and I guess as well that depends on the kind of the area where the system is deployed. So I talked about trading algorithms, and so there's a reason why they lead the world in terms of kind of deployment and autonomy, because the action space is very limited, and the things that the kind of side effects are actually limited. But having said that, still I haven't seen any trading algorithms which kind of look at side effects at all. So even in a very limited area like that, it's a huge challenge to try and build up a world model where you start kind of taking account of your impact on the system.
Well, I know in the case of trading models, there are elements of side effects which are even classically looked at, which are, you know, like market impact, or trying to stay away from things like front running or things like that, which may or may not be, you know, explicit constraints on achieving the objective, but are still things that are still like sub-objectives or secondary objectives, typically.
I guess if you, oh, sorry.
Sorry, go ahead.
Well, I was just going to kind of piggyback on that. Like, I guess if you think of like core versus peripheral issues, like the core issues could be kind of reflected in terms in the reward function that are explicitly discouraged, right? So if you have some penalty in there, that could be a core issue. On the other hand, peripheral things could be things that crop up that aren't explicitly modeled in your reward function, that are kind of unintended behaviors. But once you get to the real world, obviously the number of peripheral issues you could have are going to snowball. So I think we need more exploration of more realistic simulators and data sets, and then even on top of that, increased randomness in them to deal with some of these unintended things that crop up.
Maybe a very interesting perspective, maybe also to add a bit to that from the perspective of impact regularizers, because of course this is my hammer, and so I'll see everything as nails. So indeed, I think in the core world model, it would be very nice to have some explicitly specified things your agent cannot do and so on. But the more, if you go to the peripheral thing, I think what could be a really promising approach is to really be very uncertain in the beginning of all the impact of your actions. To just say, okay, my world model is quite shitty, so I'm very uncertain of what all the consequences of my actions will be. So then actually a lot of actions will be highly penalized by your impact regularizers. And so then this really active learning approach can kick in, that says, okay, if I have the possibility for a good positive reward of my specified reward function, but actually my impact regularizer is punishing it very severely, then either you can ask the designer, like, okay, I have this really huge trade-off between a possible very big gain, but I'm very uncertain about the consequences it will have. So can you give me some extra information? Or either you can then do the more active experimental method, like, okay, this seems like a very promising action I should take. Maybe I can do some small other actions to probe my world model to really lower my uncertainty about the possible impact that I will have with this action. So I think that would be quite complementary to the things you said, Jared.
The other thing I was going to say is there's a nice structure called a shield, which sits between the reinforcement learner and its kind of actual actions, and it screens actions that the RL agent chooses and then rejects them if they turn out to be illegal or dangerous. So you could, and actually I think this model is probably the way that a safe RL agent will be deployed, and that having these two systems, you can easily differentiate between kind of core side effects, which you would perhaps model within the RL agent itself, and the kind of peripheral side, which you might choose to model in the shield. So that's a nice way of or potential way of separating out the two things. So you have your core learning functions within the core RL, and then the shield, which kind of looks for this kind of wider remit for the unknown side effects. So that's the structure that I'm really positive about, and I think has great potential in safe RL deployment areas.
That's awesome.
And then I guess presumably then you would train with that shield in place so that your agent kind of learns how to work with it effectively.
Yeah, so it's a nice bridge between, it's a potential bridge between kind of symbolic restrictions and your RL agent. So at any moment in time, it can pass a set of legal actions to the RL agent without actually having to get involved in the plumbing of the learning. So that also means that you could have the difference between the systems, that you don't have to give kind of private, if for some reason your learning process was proprietary or the shield was proprietary, there's no actual kind of need to look into either system. So that's a good way of kind of two companies working together as well, I think.
Very interesting. And this shield, then, should it be always more powerful than your RL agent then, because it needs to analyze the consequences of the action of the RL agent that the RL agent itself cannot properly do then? Or can they interplay in another fashion, to say, like, because both agents, they interplay, so maybe there are some strange things happening when the RL agent will become much more capable than the shield, such that it can predict which actions the shield will make illegal, to say, such that it can manipulate the shield a bit. Do you have any comments on that? Or
I mean, there's about 3 papers that use the structure. So I guess there are some adversarial kind of implementation, kind of implications, and some things that kind of people with catastrophic views of AI might want to think about. But the implementations I've seen is that the shield has the final say on what is allowable and what isn't. So I guess they could spend time trying to trick each other. But in its simplest form, the shield doesn't have to be very, it doesn't have to have much intelligence, I don't think.
It is a challenging area, though, how you can integrate an AI agent into a larger system, right? There's a whole host of questions there. and then if you try to train it in adversarial fashion, like how you deal with not degrading its performance in like standard scenarios, right? Like it's really an interesting area.
If I may, I have a question. Maybe it's a general question, just change a little bit topic. But I think that's a question that perhaps affects many of the presentations in this session. And it's about the very setting for reinforcement learning, where you have the rewards that are typically associated with a state of an action. So, for instance, starting with with Jared, for instance, the asymmetry. You can do some things by modifying the reward, but just some things. Even you do a nonlinear modification of the rewards, there are some things that you can't do basically because rewards are associated with state and action, but they are not taken globally. So you need to do some of these things because of that. I think that for exponential discounting, it also happens, it's a little bit related as well, that you don't really have a plan, you don't really have an intention, as Hal was saying, that you can really evaluate that intention, you only evaluate the next action. And I think many of the problems perhaps are associated with this narrow view of reinforcement learning. And I don't know if some other more general models of reinforcement learning that go beyond that could be the solution, it could be an alternative.
For me, the fact that reinforcement learning works at all is a complete mystery. The idea that you can teach an agent just through a single signal, reward signal, it's just amazing to me. And even without an idea of causality, you can get agents to learn very complex tasks. But it has struck me that the task of trying to get an agent to do something complicated just through a reward stream is a big demand for quite a small signal of feedback. But I'm kind of not familiar with other methods which kind of augment the reward signal. I guess you could have kind of rewards based on other things. But yes, it would be, I would like to think there's a better way of learning than RL.
I think there's a lot of potential in model-based reinforcement learning approaches where you learn a model of that state transition, right? Like to next state. And then you could kind of explicitly plan off of that, looking a few steps in ahead, because then you have, there's still a neural network in there, but you have some intuition about what's likely to happen in the system. And it's not just like playing it forward in that Markov process, like one step. It's, thinking ahead and planning. I think in the future, we're going to see more and more of those approaches implemented on more complicated systems and maybe in conjunction with model-free approaches.
Yeah, but that doesn't go beyond the standard paradigm. You still have it. It is the agent that tries to adapt to this representation of the world that we give the agent, which is stay this MDP or you want a POMDP, but we don't go beyond that. And even there have been some, because it's harder for us just to work with that. But something that you don't assign the reward according to the state of the action, but it depends on the history. And maybe some other kind of a meta state or something, and some other. So we make the reward function more complicated. And of course, that makes things more challenging, and that breaks many of the things that we have progressed. But my question was more in that line. Of course, I agree with you that we have to go in a combination between model-based and model-free, and there's still a long way to go, and we can progress on. But perhaps especially in safety, maybe we have to go a little bit beyond the standard model, or.
Yeah, I mean, I agree. And I also think what they were talking about earlier with integrating into broader systems that have more than just that MDP in there that you're optimizing, kind of patching together different things and really testing their assurance, how they work together. I think that's one avenue you could pursue. But I don't think we have a general answer yet.
Okay, do we have some other comments from the panel, or maybe questions from the presenters to other presenters, or people, some other attendees that would like to ask a question? Now's the right time.
I have a question.
Yeah, sure.
It's Mauro. So maybe it's related to the last question. If I don't know if you're familiar with inverse reinforcement learning, but yeah. So do you think that inferring the reward function instead of handcrafting an explanatory or reward function might help solving some of these issues, the issues that we just mentioned?
I think to give the perspective of impact regularizers and this inverse reinforcement learning, I think Stuart Russell is a very big fan of this inverse reinforcement learning, where your agent is really uncertain about the reward function that it uses, and this really helps the agent to prevent a lot of side effects, because it is uncertain about which reward function that it has. So you can see it a bit as it has a distribution of possible reward functions. And so often, for example, breaking a vase or something might interfere with one of the possibilities of the reward functions you have. And what's quite interestingly, actually a couple of prominent approaches now in impact regularization is really to also have a multitude of possible utility functions or reward functions, and so that the agent needs to make sure that it optimizes its main reward function, but also remains a possibility for optimizing the other reward functions that are augmented, to say. And so this really has, I think, a lot in common with this inverse reinforcement learning framework, where you remain uncertain about which reward function you're optimizing. So yeah, that's some interesting literature I think you can look into.
What I was going to say about inverse RL is that it doesn't work for inferring intertemporal laws. So if you wanted to, if you're observing an expert demonstrating, you can't learn a kind of a law that I guess in my language, a non-state law. So a law which says if you do this, then you must do this later on, is difficult to learn through IRL. So you'd still need a kind of to program the rule directly, even through a reward penalty or a regularizer or some other method. So yeah, Stuart Russell's very enthusiastic about the method, but it has some limitations in trying to convey kind of more complex laws. And I don't know how that's going to be, how that can be kind of resolved. And I guess the other thing as well is it is a slightly ill-posed problem. So there are lots of different reward functions possible for any demonstrable behavior that you observe. So you have to make some simplifying assumptions on the type of reward function to be able to even answer the problem satisfactorily. So it's a really, really difficult problem for those reasons. So I'm not that enthusiastic about IRL, but I'm sure I'll be proven wrong.
So I have sorry, go ahead.
So it's a bit of a different question, and probably one starting with Hal. If I understood the presentation correctly, you were kind of saying that someone's going to have to be responsible for autonomous agents in that they may break the law. And I guess I'm kind of thinking, well, is that kind of the organization that makes it, or the engineers that program it, or the people who wrote the standards that the engineers are following, or the academics who did the research on which those standards are based? Where do we find the responsibility lying? Or is that an unfair question?
My point, you could have a whole conference on those questions in itself. And I'm sure there are conferences on those questions. My point is really that as engineers, eventually it will come back to us. eventually, whoever gets kind of sued or blamed or whatever, there will be a requirement as engineers for us to design safe systems. I don't really have. I'm actually kind of agnostic on who gets blamed at the moment. But as kind of programmers, it will be our task to make sure that we can design safe systems. So kind of regardless of the process in the middle, it's our job to make sure that we can find a way of deploying the system safely. Otherwise, I guess society will say you can't deploy this system safely, or the systems will be deployed in a way where in kind of very controlled environments where they can't do harm. So autonomous vehicles are fine just as long as they exist in areas where only autonomous vehicles exist. So an example of that, I guess, is if you look at the London Gateway port, which is built east of London relatively recently. The kind of trucks that move the containers from the boat into the storage area, they're all automated, and it's a no human zone inside there. So that's completely controlled. Humans aren't allowed in there, and there's fully autonomous vehicles kind of moving about. So that might be it is a solution already. So if we can't prove that we can have safe autonomous systems, that might be the only way where we actually are allowed to deploy them.
Wow. Can I make a comment here? Is that okay?
Yeah.
Please. Yes. I'm a software engineer, have been one for a couple decades in the United States. And on the, I just left a conference on ethics and AI. And one of the big points that was made was that in the United States, we don't have a requirement that software developers have a standard license or any kind of standard certification. We don't seem to have a shared body of knowledge even between our universities. A lot of the computer science programs are, in various departments. They have different methodologies, different bases, different ontologies. And so it gets very, very difficult to regulate the whole enterprise of software development, of software engineers, when you have so many different methodologies and so many different approaches, and none of it is at the penalty of jail time or fines. We're not like the architects or civil engineers or mechanical engineers. We kind of have like a wild, wild west going on. And so it's a very difficult proposition in safety and AI when we don't even have a shared definition for what it means for a piece of software to be correct. We have various academic definitions, but we don't have legal definitions. And let me throw one more thing in. I'm in the state of Ohio, and we were trying to start an association of software engineers here. And the state of Ohio forbid that, they denied that application because they don't have a recognized definition of software engineering. There was no standard for it. So I don't know that we can get to anything like safety at the, state and federal level until you have some kind of legal obligation on software developers at all levels, really.
So we are doomed, and we expect for a definition of artificial intelligence. We haven't managed for a definition of software engineer.
Yeah, that's exactly the case, because at the end of the day, all of the tools that we use in AI research and in deployment, all those tools boil down to some kind of software hardware system that's been implemented. And if you have 50 different models for implementing some kind of system and no standard vocabulary for what we're talking about, what it means for something to be correct, or how to verify the software or validate the software, and how do you write regulations? How do you get to labor law you know, how do you get to contract law? How do you even articulate these things if we don't have something at the state and federal level that says this is what this thing means and here are the consequences if you don't abide by this? And in the United States, some states have something. In Ohio, we have nothing. You know, and so any developer can develop anything. And then we have these end user license agreements that really absolve us of any kind of responsibility. It's not our fault. You know, if you look at the fine print, we are not accountable for anything software developers. So, you know, we have a very tough road to hoe, so to speak, before we get to SafeAI if we can't have an agreed definition of what software engineering is.
I think, Cameron, we need more kind of case law and examples and actual these things need to be tested in court to actually kind of establish where the responsibility lays between programmer, owner, employer, and it's just there's really very few court cases. So everything's up in the air. So really, and I don't know who's going to bring legal action to start establishing things, but it is very much the Wild West, I think, at the moment until some laws are established. And if you look at, you can look at the fatalities that the autonomous cars have caused already, and there's things you can read into there. But yeah, in the next 10 years, it's going to be very difficult. And part of it is an ambiguity as to what software, is it a product or is it a software? And those two things are regulated separately as well. But yeah, very chaotic times. So hopefully in 10 years time, we will have some more answers and some more law, but until society gets around to deciding, we kind of don't know yet.
Maybe this is a good point for Richard to say a few words about an initiative that goes a little bit in this direction, which is a clear initiative, which is about finding common ontologies, terminologies, and definitions in the area of AI safety. Richard, are you there?
Yes. Thank you, Jose.
Would you like to say something around about this initiative? I think it goes very well with these comments about.
Yeah, that's an excellent point. Thank you for raising that. So there is an initiative that actually spun out of some discussions around the workshop, the same workshop last year, called the Consortium on the Landscape of AI Safety. This is a new endeavor, just founded in January, where it's a bunch of different organizations of different types, and I am starting to share my screen here, that are working on creating a landscape of the field of AI safety. So AI safety is actually a bunch of different fields, and there are lots of different kinds of views that come from different subfields, different disciplines, different individual organizations or people. And really what this is about is mapping these views and bridging these views, of forming interconnections so we all understand the terminology that we're using and also the concepts. This kind of thing also helps to find unknown unknowns in one's perspective on the space of AI safety by seeing what white space is not connecting. And so here are some quick views on some of the default things. So very high level, we're trying to address all the different kinds of topics within the field. So this goes from agent foundations all through things like governance and everything in between. So certainly everything that this workshop addresses is quite relevant. The knowledge graph, again, multiple layers, will be outputting things like documents and trees, checklists, syllabi, mind maps, guidebooks, research agendas, these gap analyses, application-specific safety reports, and various kinds of technical diagrams. So it's, again, a consortium that includes universities, companies, nonprofits, and government entities. And so there's a wide variety of different kinds of benefits. Again, understanding the blind spots and what demand is out there for what type of research. Improving the visibility and the consumption of one's own research, or trying to highlight various kinds of research you think are important. And it also helps a lot with public education and outreach, and just generally moving the whole industry forward. So if you are interested in what I'm describing here, please check out our website, which is up there, clay.org. CLAIS.org, and you can also email membership@clay.org to inquire about joining. Thanks.
Thanks, Richard. Maybe it's time that we, I don't think we are going to be blamed for all the havoc that AI is going to create in the future, but as workshop organizers, we have to keep our time. So maybe we can move to, unless there's any question about Clay that you would like to ask, or maybe we can move to Huáscar, and maybe we can just go to the closing remarks.
Okay, thank you very much, everyone. Just a reminder before finishing, yes, actually we plan to talk a little bit about Clay. So the comment was very asserted regarding this. So as you know, we pre-selected 6 papers. If you want to vote, you have, I think, 1 minute to do it. While we are closing. I would like to thank all the chairs. I think we are 4 chairs right now: Xiaowei, Chen, José, and myself. And in the morning, we had also Cynthia and Xiaowei, I think, and Richard is now, sorry. So Jean and Mauricio were not able to come here, but they worked hard also to help us in preparing the workshop. So as you know, we also organized another workshop in hÉigeartaigh. And I think, as Richard said, many of these discussions in the last years helped us to initiate this initiative called CLAYS, and we hope you can join us as well. So I don't know, the other chairs would like to say something before I show the final results, the best paper award.
Drum roll. Let's go for the drum roll.
Go ahead. And the winner is?
Okay, so I will show in just a second the results. I don't know if you can see my screen. So there were 6 candidates, and the selected paper is an evaluation of crash prediction network, CPN, by the main author is Sasha. So congratulations to the authors, and we will send you a digital certificate to you in the next days. We also plan to publish all the presentations and the videos in the upcoming weeks. I think I hope in the next week it will be ready.